Right. Maybe let me not have this jacket on. I hope everybody is trickling in. Thank you. Thank you. All right. You seem very impressed with yourself.
Absolutely.
No, thanks.
I find my passion. This is fun. Yeah, man.
We got a technical team. All right. Just give it a.
Just give me a shout out there.
All right. Right, I hope that we are getting more people in. Right, I just want to make sure that I can also see your comments. We're going to start in just a few. Looks good. Looks solid. All right, we've got a solid 102 people joining us at the moment. Maybe I think, Jeff, for the sake of isolating sound, maybe you'd want to, yeah, please. Yeah, sure. Good afternoon, Tulu. Hey, Kulu says paper one was lit. Okay. All right. All right. Good afternoon, everybody. Once again, your favorite uncle is with you. Hey, I see you guys are so excited about paper one. That it was really, really lit. Firstly, I'd like to, he said I should give a shout out. I've got a member here of my team, Sbonelo Manzini, and by the way, he's a graduate now. So, yeah, congratulations to him. Right, so I've got a very, very strong team with me here. All right, thank you, Smo. All right, so, now that you've written paper one very well, I'm so glad to hear the feedback that I got. Funny enough, I didn't get feedback from my own students that are in my class. They haven't really told me about it. Yesterday was a hectic day, but now we are ready for paper two. Guys, I think there are just some sections in paper two that I've really identified as being problematic at times. So what I'm going to do today, I want us to look at rates of reactions. That's the first one. I want us to look at chemical equilibrium. And I want us to look at acids and bases, as the last one that we're going to look at. Now, if time allows, we've got Didi Malang, who's just given us a love gift. Thank you so much, Didi Malang. I really appreciate that. I love the fact that you guys find value in what I do. Really, guys, you can if you want to. This is not something that we compel you to do, but for those of you who want to give us their super chats, their super stickers, there's other ways in which you can thank us for the work that we do. But I also want to say, for those of you that want to become members of this channel, those of you that might still be wanting to write your maths and science exams, we've got the academic bus. You can be a member, and just for a very minimal fee. I forget about our fee structure. I think there's a 20 Rand membership There's also, I think there's a 60 Rand one and there's a 100 Rand one. And for the 100 Rands per month, you are now going to be able to get maths and science lessons so that they actually help you to cover the content as we go along. So, like Tepo said, let's cook. All right, I like it. I am going to, in future, be doing these also for grade 11, for those of you that might be watching. So please tell your cousins, your friends, everybody that uncle is doing the things. All right, now let's get right into it. So I picked the past paper from November 2024, right, as where we are going to really start. Okay, so this is Department of Basic Education, so that's a DBE paper, but I'm going to skip organic chemistry. Maybe if we have enough time, I might go through it, but what I'm going to do is I am going to just skip to question 5, start with rates of reactions. I'm going to cover chemical equilibrium, and if we have enough time, we are going to be looking at acids and bases, and then we can come back into especially reactions in organic chemistry. So enough yapping from my side. Let's go right into it. I hope you don't mind. I won't be covering in this case the theory part, that is the definitions and so on. I'll just glance through them, but let's go for it. Okay, right, now the question says, the reaction between pure aluminium and excess, now please, I want you guys to note, they said excess hydrochloric acid. Now remember, every time that they say that to us, by virtue of saying that hydrochloric acid is in excess, it now suggests that aluminium is the limiting reagent, right? So which means in this reaction, if the reaction stops, it will be because we've run out of aluminium. So that's very important. Okay, right. Now they say to us, excess hydrochloric acid is used to investigate the factors that affect the rate of the reaction. Now note in this case, we will be looking at the factors that that affect the rate of the reaction. Right, now the first question says the balanced equation for the reaction, right, it's given over there. Now they say define the term reaction rate. Now remember that when we define reaction rate, that's the change in the concentration of reactants used, or you can say products formed per unit of time. Okay, now they say in experiment 1, in this experiment, 1 mole per cubic decimeter of hydrochloric acid solution reacts with 0.5 grams of aluminium strip, right, from the aluminium roll at room temperature. So they give us the concentration of hydrochloric acid, okay, and they also give us the mass of aluminium. And now I want you to keep remembering that aluminium is our limiting reagent. They say the graph of volume versus time for this experiment, not drawn to scale, is shown below. Right, now, they say to us, for the time interval 0, t is equals to 0, to t is equals to 5 minutes, the average rate of for the formation of hydrogen is 0.03 cubic decimeters per minute. Now, guys, I please want you to note the following, that when you're talking about rate, we need to check first. So the rate of reaction in this case is given in cubic decimeters. So in this case, it means we must have said it's the change in volume divided by the change in time. Okay, right, so that's the change in volume divided by the change in time. Now, I want you guys to note, so that would be for the formation of hydrogen, right? Now they say to us, calculate the mass of aluminium present in the container at 5 minutes, right? And they said the molar gas volume is 24.3 cubic decimeters per mole, right? Now, ladies and gents, what I'm going to do, let's go back to rates of reactions, right? So actually, let me write it down on the other side. So I'm going to say, right, the rate of this reaction, I hope that's visible, is equal to the change in volume divided by the change in time. Okay? Now, how did I know that it's the change in volume? From the SI units, right? And my time will be in minutes. I don't need to convert those to seconds, right? So the rate of reaction is said to be 0.033. Okay, so that's 0.033. Right, so that's change in volume. Okay, so in fact, let me say volume final, V final minus V initial, divided by the time. Now the time, I will leave it in minutes, so that's going to be time final, which is 5 minus 0. Now if you notice, this is going to be a fraction, so we can cross multiply, right? So 5 minus 0 gives us 5, and if I cross multiply, 5 multiplied by 0.033, okay, so I'm going to just use my calculator, 5 times 0.033, right? When I cross multiply, note, all I've done is convert this into fractions, and so I'm cross multiplying. So our initial volume, remember, we would have started with 0, right? Because right at the beginning, you didn't have any hydrogen. So you started with 0, and at 5 minutes, you had something. Right, so which means our volume final, in this case, will be 0.033 times 5. And so that means that this is 0.165. Note it is volume, that is cubic decimeters. Right. Now this is the volume of hydrogen that has been formed, right? Now guys, in this section, I really want you to note the importance of stoichiometry, right? So I've got the volume of hydrogen that has been formed. Let me convert that to number of moles. So the number of moles will be volume divided by molar volume, right? So that's 0.165 divided by. The molar volume has been given to me as 24.5. Now, if they had said that we are using standard conditions, then we know that the molar volume would have been 22.4. That is always given to us. So in this case, this is going to be 24.5. And so the number of moles that we get there, okay, in fact, I shouldn't have removed that. So that's 0.165 divided by 24.5. And so what I am going to get there is 0.00673. And you can continue that. This is going to be moles. Right. So that's the number of moles that I am going to get for hydrogen. Now, what we do is we go back to the reaction. This says for 3 moles of hydrogen, I am going to use or require 2 moles of aluminium. Now, please, I want you guys to remember this, right? So for every 2 moles of aluminium, I'm going to produce 3 moles of hydrogen. So the question is, okay, I'm going to just write this. I'll look for space somewhere. Okay, if you don't mind, I'm just going to write it here. So for 2 moles of aluminium, I'm going to produce 3 hydrogen. This is from the reaction. So the question is, now remember, I've got moles for hydrogen here. So for how many moles of aluminium will I get 0.673? And what am I going to do? Cross multiply. So when I cross multiply, I'll say 3 multiplied by n is equal to 2 multiplied by that entire thing. So eventually, what am I going to get? Okay, right? So if I continue that over here, that will be 3n is going to give me 2 times that amount that I had, right? And I'm going to divide both sides by 3. So the number of moles of aluminium that I'm going to get will be 2 over 3 multiplied by that value. So that value that is given multiplied by 2 over 3. So all I've just simply done is I've cross multiplied there, all right? And please, if you've seen how I do stoichiometry, you'll note that I always do that method, that we call it ratio and proportion, right? It's just that I'm struggling with a bit of space here. So we said for every 3 moles, or rather for every 2 moles of aluminium, I get 2 moles of hydrogen. So for how much will I get 0.006, that amount that we've got, 673, right? And what I did was to cross multiply, and at the end of the day, we said, well, if I cross multiply, it means that 2n is equal to, so 2 times n, rather 3 times n. So that's 3 times n, right? Yeah, so that's 3 times n is equal to 2 times 0.0673. And if I divide both sides by 3 on either side, I will multiply that by 2 over 3. So the number of moles of aluminium, I multiplied by 2 over 3, and I got 0.004 and other things. Now, in this case, remember, they had said calculate the mass of aluminium, right? So I'm going to proceed right to my periodic table and find aluminium, right? And you'll see aluminium has a molar mass of 27, right? So I am now going to say, all right, now to find the mass of aluminium, all I'm simply going to do is say, well, number of moles, okay, I'll write it over here. Number of moles is mass divided by molar mass. So that's 0.0044. That amount that I have on the on my calculator is mass divided by 27. And I am just simply going to cross multiply. So the mass is going to be that amount multiplied, okay, let me just write that properly. Okay, that's multiplied by 27, and I find that mass to be 0.12 grams. So that's the amount of aluminium that I am going to get. And guys, I really want to, at this stage, you know, I cannot emphasize this enough for you to actually get familiar with using stoichiometry. I've got videos on stoichiometry. You can have a look at those, and they do help quite a bit. All right, now let's go on to the next portion. Right, we've got a lot of writing that we've done. So this was 6 marks, so definitely worth it, okay? So they say to us, assume that the concentration of hydrochloric acid stays constant during the duration of the reaction. So in this case, they say, use the collision theory to explain the change in the reaction rate between T0 and T is equal to 5. Now let's note what happened to the reaction rate. Okay? So if we note there, we started with a higher reaction rate, but what's happening? It will actually begin to slow down, right? So they said we must assume that hydrochloric acid stays the same for the duration of this period, right? Now, what are we going to say? We say, well, in this case, we've got a higher concentration, right, of reactants. So, in this case, a decrease, okay? So, we're going to say a decrease in aluminium, right? Remember, we are seeing that the rate of reaction is decreasing over time. It starts at a high rate, but it decreases as it goes. So in this case, a decrease in the number of moles of aluminium, right? So a decrease in the number of moles of aluminium will decrease, in this case, the number or the volume per second, right? Will decrease the volume, or rather, let me say, the number of moles per unit volume will decrease the number of moles per unit volume all right, and so in this case that will decrease the number of collisions per second, or you can say now there'll be less moles that have the correct orientation, okay, and that will decrease the number of effective collisions per second. If you'll allow me, ladies and gents, you can replay this as many times. I won't be able to write that down, all of it, but I hope that you got the gist of it. Okay, right, so what we are seeing there is that over that 5 minutes, we start with a high reaction rate, but it keeps decreasing, right? But in this case, we notice that a decrease in the number of particles of aluminium, right, we'll see a lesser rather number of moles per unit volume, and that will decrease the number of collisions per second, and as a result decrease the rate of reaction. Okay, right, now they say to us, assume, okay, we've already covered that, so they give us experiment 2, and I hope you don't mind. I'm just going to remove the stuff that I did here, calculating for the number of moles of aluminium. And I'm going to go about just to check your questions, if there are any questions that I see. Okay. Nkosi says, I can't wait to see acids and bases and equilibrium. We're coming. We're getting to that in just a little while. Right. So experiment 2, they say. Experiment 1 is repeated. Now they are using 2 moles per cubic decimeters of hydrochloric acid. So what are we changing, ladies and gents? We are changing the concentration of hydrochloric acid. Initially, we're using 1 mole per cubic decimeter, and now we are increasing that to 2 mole per cubic decimeters. Now they say to us, redraw the above graph, no numerical values, right? No numerical values need to be shown in the answer book, and label the curve as A, right? On the same set of axes, draw the curve that will be obtained for experiment 2, label this as B. Now, firstly, let me caution you with one thing. Remember that aluminium is the limiting reagent. So I'm going to use the very one that is given here. So you were going to draw the very same one that you are given over here, right? So they said we must label this one as A. So this is for the original experiment 1. So that's graph A. Now for B, I am going to get a higher rate of reaction, but I'm still going to produce the same amount. I'm trying to make my graph a little bit better. Okay. All right. I hope you get it. Okay, I'm trying to make my lines as straight as possible. Right. So this is the kind of graph that I'm going to get. So this is graph B. In fact, let me do this. So this would be A, and this would be graph B. So the rate of reaction will be higher for graph B. Why? Because we've got a higher concentration. And we know that an increase in concentration, in this case, will now have more reactants, or rather will increase the number of particles per unit volume, right? That will now cause for there to be more frequent collisions per second, and that will definitely increase the rate of the reaction. Okay? Now, we will not produce a higher amount of hydrogen. And why is that? Because in both instances, we know that aluminium is actually the limiting reagent, right? So we will produce the same amount of hydrogen, but if hydrochloric acid was the limiting reagent, then in that case, for graph B, we would have been able to produce a higher amount of, a higher amount or higher volume of hydrogen in that case. So that is how the cookie crumbles. Right, now they give us the third one. They say experiment 1 is repeated using 0.5 grams pure powdered aluminium. So what are they doing? They are now increasing the state of division of aluminium. And definitely we know once you break it down into powder, it is going to increase the rate of the reaction. Now they say to us, how will the volume of hydrogen produced in experiment 3 compare to that in experiment 1? Okay, now I want you to note in this case, the amount of aluminium is still exactly the same. The only difference is that now we are going to have an increased rate of reaction. But again, the number of, the amount of hydrogen that will be formed will actually be exactly the same, right? And in this case, the only difference is that the rate of the reaction will be much faster with powdered aluminium. Now they say to us, actually we were supposed to choose from that greater than, less than, or equal to. And our answer is equal to. And the reason for that, ladies and gents, is because even initially we were given 0.5 grams of aluminium. The only difference is that it was given to us as a strip. Okay, right, now let's go to the next section. They say to us, the next section is over there. Right, now they say curve X is the Maxwell-Boltzmann distribution curve for the reaction under a set of reaction conditions. A change was made to one of the reaction conditions to obtain curve Y. So we are assuming that curve X is our original, right? But what should we have done to obtain Y? This tells us that curve Y, for curve Y, we actually increased, in this case, the temperature of the reaction. Okay? Right. Now they ask us, what change was made to obtain curve Y? Right. It was an increase in temperature. Okay? So note this. Every time you increase temperature, right? Look, I don't have the time to explain this now, but what we will do is that will result with a lesser peak, but you have a wider distribution, right? So in this case, what happens is that there are more moles that are now able to have, in fact, your average kinetic energy will increase, right? Where your peak is, it's now shifted to the right, okay? So in this case, we've got more moles that have a higher average kinetic energy. And they say to us, give a reason for the answer in question 5.2.1. So our reason is that an increase in temperature will increase, increases the average kinetic energy. Average kinetic energy. Now we don't need to get to go to town with this because it's only for 1 mark, right? They didn't say we must use the collision theory, but in this case, you'll see that for curve Y, the average kinetic energy is over there, whereas for curve X, the average kinetic energy is over there. So definitely it tells us that we have increased temperature. All right, I hope that this makes sense, guys. Let's move on to the very next question. All right, let me just check quickly if there are no questions that were asked. And Nkosinathi says on Monday, Mele Silwele abo 100 and something. I do agree, Nkosinathi, you must fight. Okay. All right. Okay. So I'll keep looking here so that I can see what your questions are. And please, guys, don't be afraid to ask those questions. That's the whole point of this section. I see my team is actually giving you the past paper where you can get this past exam question paper, right? Yeah, you can click on it. The link, rather, is on the description. Not rather the description, but on the chat, on the group chat for this. Okay, right. Now let's go to the next section. All right. Now, I hope Nkosinathi, you are excited. Let's go for it. They say the reaction of carbon monoxide, right, with oxygen is investigated. The reaction reaches equilibrium. Okay, let me take some water. Okay. They say the reaction reaches equilibrium in a closed container. So very important that we have a closed container because remember in this case we've got gases, so we don't want any of the gases to escape. It must be a closed system, right? Right, they said at a temperature T degrees Celsius according to the balanced equation. So we've got the balanced equation. By the way, delta H less than 0 tells us, I always use that Pac-Man, adage, right? So if you look at our Pac-Man is facing to the right. So that means energy is on the right-hand side. This means the forward reaction is exothermic. And if the forward reaction is exothermic, then it means that the reverse reaction is endothermic. Okay, so they say changes to the conditions. So there we are. You can see on the graph, a graph starts with all the amounts being constant, right? What does it mean? It means we are at equilibrium, right? So it's important for us to be able to interpret this graph. So they say changes to the conditions of equilibrium are made at different times, right? The graph shows the results obtained, right? X, Y, and Z represent the gases in the above reaction. Now, they said to us, define the term chemical equilibrium. Remember that this is when the rate of the forward reaction is equal to the rate of the reverse reaction. So they say to us, use the graph to answer the questions below. At T1, oxygen was added to the container. Write down the letter that represents oxygen. Now, you can see at T1, guys, when I look at at those graphs, which one was like literally went up. Okay, that's definitely X. You can see at time T1, right? It literally went, it shot up. It says to us that we introduced oxygen, right at the beginning there, right at T1. So that means they said choose X, Y, and Z. It is definitely going to be X. Now, I want you to also note the following, right? So they are saying X represents oxygen, and oxygen is a reactant, okay? Right. Now, after we introduced oxygen, now we are going to have a change in the amounts in accordance to Le Chatelier's principle. And remember, what does Le Chatelier principle state, right? If one of the factors that affect equilibrium changes, then equilibrium will oppose the change. So you can see, I added more oxygen, and what does equilibrium do? It opposes the change. It now decreases the amount of oxygen. It favors the reaction that uses up oxygen. So oxygen will begin to decrease, but it means that carbon monoxide will decrease. So that tells me this Z here must be carbon monoxide. Okay? And obviously, it therefore says that Y must be CO2. Okay? Because will favor the forward reaction, and as a result, it means that carbon dioxide will actually increase. You can see that is exactly what happened after we increased the amount of oxygen. Now, guys, if you're still struggling with this section, I would strongly suggest that you go onto our playlist on chemical equilibrium, and you will see there's a nice way in which I actually explain it, and it will really, really assist you. And Kosnati, you'll be able to get those hundreds in that way, okay? Right, now let's go to the next question. They say at T2, pressure is adjusted by changing the volume of the container. Was the pressure increased or decreased? Now let's go for it. I want you to note, this is a graph of concentration against time. Now, if I look at it, remember that concentration is number of moles divided by the volume, right? So that's number of moles divided by volume. So that tells me in this case, I didn't do anything to the number of moles, but I certainly did something to the volume. They are inversely proportional to each other, right? Let's start there. So in this case, if I were to increase the volume, that will decrease the concentration for all of the chemicals that you've got there, right? Reactants and products alike. So you can see all of them just simply decreased sharply at T2. Why was that? It was because in this case we increased the volume. What does that mean? We decreased the pressure. The only way in which I can decrease the volume in this case, rather we increased the volume, right? The only way in which I can increase the volume in this case is to make the container bigger, right? And if I make the container bigger, it means that the concentration becomes less for all of them, right? Now, I'll show you as well. Now, if I decrease, or in this case, if I increase volume, I decrease pressure. Actually, let's answer that question. So the pressure was decreased. Okay? Right. And they said to us, give a reason for the answer in question 6.1.3. So we say in this case, when pressure is decreased, right? When pressure is decreased, it means that volume is increased. An increase in volume will actually decrease the concentration of all of the gases. Okay, right? A decrease in concentration, an increase in volume will decrease the concentration of all of our gases, right? So we know in this case, we know that we decreased the pressure, right? But here's another thing that I want you guys to note. Whenever you are going to decrease pressure, you are making the space smaller, right? You are making the space bigger. When you decrease pressure, you are making volume bigger. So your reaction, what you always do at equilibrium, you're going to check where do you have a higher number of moles. When you make the space bigger, equilibrium shifts to the side that has higher moles, right? That occupies more volume. I see I've got 2 plus 1, so I've got 3 moles of gas on this side. Whereas on the right-hand side, I'm going to have 2 moles of gas. So once I actually decrease pressure, that is by increasing the volume, equilibrium will shift to the side that has more moles, it occupies more volume, so therefore equilibrium will shift to the left, or you can say the reverse reaction is favored, okay? And you can see in that case that afterwards, okay, carbon dioxide started to decrease. You can see there. And obviously my reactants therefore started increasing. Okay, right, and the next question, they say write down the name or formula of the gas that is represented by letter Z. We've already said that definitely has to be carbon monoxide, right? Why is that? Because we realize in this case that it actually is part of our reactants. So if oxygen is the one, then it means that carbon monoxide must be the other one. It has a similar trend and pattern with oxygen, so that means that it is carbon monoxide. So we definitely know this is definitely CO. And they said, give a reason for the answer in 6.1.5. I can say that it shows a similar trend. Shows a similar trend. Okay, so it shows a similar trend with oxygen. All right, and that means that it is a reactant. Okay, right. Of course, we expect that reactants in this kind of graphs should kind of behave in the same way. Right, now, then the next section, 6.1.7, they say to us, what change in temperature is made at T3? Choose between increased and decreased, or decreased. Now, let's go to T3. And I want you to please remember, ladies and gents, right? What I'm going to do, I always just check the products. My product in this case is carbon dioxide. So whatever change was made to temperature made carbon dioxide to actually increase. Okay? So the amount of carbon dioxide increased. So which means the change in temperature that was made must have favored the forward reaction. Okay? Now I want you to note, remember that the forward reaction, we said that the forward reaction is exothermic. And I want you to remember that it's a decrease in temperature that favors the exothermic reaction, right? So in this case, it means if I say heat is on the right-hand side or energy is on the right-hand side, when I decrease what is on the right-hand side, then equilibrium tries to replace, right? So in this case, a decrease in temperature will favor the forward reaction, okay? And in that case, that is how we end up with more products being formed. So it was definitely a decrease in temperature. All right. Now I love the fact that they go on to the next one. Use Le Chatelier's principle to explain, right? So firstly, we say you state the change, right? So a decrease in temperature okay, so a decrease in temperature favors the exothermic reaction right? That's a statement of fact, right? A decrease in temperature favors the exothermic reaction. The forward reaction is exothermic. Okay? Therefore, the forward reaction is favored. Okay, so the forward reaction is favored. Okay, and now we take it back to the graph. And this is what results, in this case, in more carbon dioxide being formed at T3. Okay, right, and I please want you guys to be mindful of that. So every time that we increase temperature, we favor the endothermic reaction. If we decrease temperature, we're going to favor the exothermic reaction. Okay, right, now let's go on to the next question. Right, and this is our dear friend, okay, where we are now going to be looking at the calculation of Kc. They say to us, carbon monoxide reacts with water, water vapor, H2O at T degrees. The reaction reaches equilibrium, chemical equilibrium according to the balanced equation. Right, now they say initially we've got 0.6 moles of carbon monoxide and 0.6 moles of H2O. 0.1 moles of carbon dioxide gas, right? And 0.1 mole of hydrogen. Now we start with specific amounts. So I am going to draw my rice table. Okay, I hope that you can see this. And please guys, when you draw this table, always remember to write down the SI units, right? So I've got 4 things there. All right. Okay, so I'm going to have initial. This is in moles. This is change. That's in moles. That's equilibrium. That's in moles. And that's equilibrium concentration. And that's in moles per cubic decimeters. It's important for us to insert the SI units. Okay, so let's go for it. Now, I know some of you prefer to always write down the that column for ratio, right? Nothing wrong with that. I'm just going to put that there. So this is 1, this is 1, this is 1, and that's 1. Okay, that's the balance reaction. So that's CO, that's H2O, that's CO2, and that's H2. Right. Now let's start with what we had at the beginning. They said we started with 0.6 moles, 0.6 moles of this guy, 0.1 moles of carbon dioxide, and we've got 0.1 moles of hydrogen gas, right? They say they were mixed and sealed in a 2 cubic decimeter flask. Right. If the equilibrium constant of this reaction at T degrees is 4, calculate the mass of carbon dioxide present, right, in the flask at equilibrium. And now, guys, this is where we are now going to have to do a lot of gymnastics, right? Now, I want you guys to think about this very carefully. What I decide to make X in this reaction will make or break, right? So in my case, this is what I'm going to do. There's nothing that I can do for the rest of this table, right? But what can we therefore say? Let's assume that the number of moles of carbon monoxide that were used, right, during the course of the reaction is X. So if I make this X, okay, now remember this is on the change in moles. The change in moles is now going to be the one that I'm now going to rely on to get the others, right? And what do I say? For every 1 mole of carbon dioxide or carbon monoxide, I will use 1 mole of H2O. So for X, I will get X, right? For every 1, there's 1. For 10, there'll be 10. For 15, there'll be 15. For X, there'll be X amount. Remember, you only use the ratio for change in moles. You do not use the ratio anywhere else. So that means also carbon dioxide will be X because the ratio is 1:1. And also it means that for hydrogen, you'll also have X because it's 1:1. Now, very careful, ladies and gents. So, right at the end, what do I have? I started with 0.6. At the end, I've got, I started with 0.6. I use, remember that carbon monoxide is actually my reactant. I started with 0.6. I use X amount. What do I have at the end? 0.6 minus X. I started with 0.6, I use X amount, again 0.6 minus X. I started with 0.1, I produce, remember that's your product, so you are actually forming it. So I started with 0.1, I produce X amount, at the end I've got 0.1 plus X. And obviously hydrogen as well, the same, it's a product, so that's 0.1 plus X. I hope this makes sense to all of us, guys. Right. Okay. Zitulele says, Grootman, Itaola. All right, so in this case, we've got a volume. Our volume was given as 2. So that means number of moles at equilibrium divided by the volume. So that's going to be 0.6 minus X divided by 2. 0.6 minus X as well divided by the volume, which is 2. 0.1 plus X divided by 2. 0.1 plus X divided by 2. Right, and now we go to our KC expression. All of them are in gaseous, gases, so that means that we are going to include all of them in our expression. So that's the molar concentration of our products. Which ones are our products? That's carbon dioxide multiplied by H2, right, raised to the exponent of 1, because remember our coefficients are 1, right? This is divided by the molar concentration of our reactants. So that's going to be CO as well as H2O. All of them are gases, so we are going to include them in our calculation. So we are given there that our Kc value is 4, right? Now, I want you to note, both your reactants, right, have got similar amounts. So that's going to be your products rather, 0.1 plus X over 2 times 0.1 plus X over 2. So I might as well say that's squared. That's divided by 0.6 minus X over 2 times 0.6 minus X over 2. So that's, we might as well say 0.6 minus X all squared. And all of this is equal to 4. Now, I want you to note, guys, what I can simply do to make my equation easier is to take the square root on either side. All right? I don't need to necessarily say plus or minus, because obviously for our Kc expression, we will get a positive answer. So, to answer this, we're going to say, right, this is 2 is equal to, that's 0.1 plus X over 2 divided by 0.6 minus X over 2. So, what I can do is, in this case, cancel my denominators. You can multiply by 2 over 2 on the numerator and the denominator. It's the same as multiplying by 1. So what it will do is that it will cancel out that value. Now, I'm trying to get some space so that I can continue with my calculation over there. Okay? So what do I have? I've got 0.1 plus X over 0.6 minus X, which is equal to 2. And so for my X amount in this case, let's say 0.1 plus X is equal to 2 times 0.6 minus X. Sorry, I'm just scrambling for space there. Okay, I might have to remove some of the things. Right, so 0.6 minus X. So what do I have? I've got 0.1 plus X, which is equal to 2 times 0.6, that's 1.2. That's minus 2x. So what I'm going to do is take the 2x to the other side. It becomes 3x. And I take the 0.1 to the other side. Then I have 1.2 minus 0.1. That will give me 1.1. And if I divide by 3 on either side, I am going to get x is 1.1 divided by 3. I get 0.37. Okay, I'm going to round it off to 0.37. And now remember, X was the number of moles that changed, right? So that's not what they asked us though. They said calculate the mass of carbon monoxide present in the flask at equilibrium. Carbon monoxide present in the flask at equilibrium. Okay, and they said the mass. Now, for me to get the mass, I now know what X is. So the number of moles, if you don't mind, I'm just going to remove this. So the number of moles of carbon monoxide at equilibrium is 0.6 minus X, which is 0.37, and that would give me this is me being lazy, 0.23. Okay, so that would be 0.23 moles, but they wanted the mass. Okay, so I'm going to say number of moles is mass over molar mass, right? Or in this case, I can simply say mass is number of moles times the molar mass. So that's 0.23 into, now note, this is carbon monoxide that we are talking about. Carbon from the periodic table is 12, oxygen is 16, right? So that's 0.23 multiplied by 28. And I get a mass of 6.44 grams. Okay? Please, if you can verify for me if that is exactly the answer. Why Jadine asked, why are we dividing by 2? Remember, we divided by 2 because we are saying concentration. Remember, here we use concentration. When you calculate Kc, you do not use number of moles, you are using concentration. And remember that concentration is number of moles at equilibrium divided by the volume, and that volume was given to you as 2 cubic decimeters. I hope that answers your question, Jadine. Okay? All right, and Tsilane says, isn't what we did on the right, we should do on the, or what we, yeah, what we, I suppose what we do on the left, we do on the right. Why are we multiplying by 2 divided by 2? Now I want you to think about it. What I did mathematically, if I multiply by 2 over 2, I'm simply multiplying by 1. And remember that 1 is a multiplicative identity. Anything you multiply by 1 remains itself. Now guys, there are so many ways that we could have approached this mathematically. Please choose your own way. I think the most important thing was the formulation of the table, right? And for me, I mean, it's neither here nor there how you want to go about this in terms of, tackling it from a mathematical perspective, but we still will arrive at the same answer. I can promise you that much. Okay, right. I hope that makes sense, guys. I am going to move on from this. Yay! It looks like we are just in time. So we are going to do acids and bases. I think we might have some time for us to be looking at another section. Okay, right. So what I'm going to do is move on to acids and bases. Okay. Gosnati says this topic is simple. I love how you feel about that. Okay, right. Neliswa says, Nkosi Mhlekazi, you are most welcome. All right, now let's go on to the next portion. They say to us, right, hydrated potassium carbonate. Okay, if you don't mind, let me get some more water. Right, they said hydrated potassium carbonate. That is, there it is there with a hydrate, is a weak base. A solution is prepared by dissolving some of this in solid water, or rather this solid in water. Define the term weak base. Right, so remember that a weak base is one that dissociates partially in water, right, to form a low concentration of hydroxide ions, right? Or you can say that it dissolves, it does not dissolve completely or dissociate completely, rather, in water, right? It does not dissociate completely in water, to form a low concentration of hydroxide ions, right? Let's go to the next one. They say write down the formula of the conjugate acid, okay, of the carbonate ion. Now, guys, I want you to please note this, right? So if I say to you a conjugate acid, so I'm assuming that these two are going to react with water, right? So that means if I say to you CO3 2 minus plus H2O, now note, it cannot contribute, right? It can't give us an H plus. So what are we going to have on the other side? HCO3. Now remember, we started with 2 minus. Now this is going to be HCO3 minus, and this is going to give us plus OH minus. So which means if you looked at water there, water donated an H plus, right? And so became OH minus, okay? In this case, in the case of CO3 2 minus, it became HCO3 minus, okay? So it acted as a base there. So that means that HCO3 is actually a conjugate, right? So they said write down the formula of the conjugate acid. So that will be HCO3 minus. I hope that makes sense, ladies and gents. Right, we go to the next one. They say to us, a hydrochloric acid solution, right, of concentration 0.1 is titrated with a prepared potassium hydroxide solution, right, of unknown concentration. So we don't know the concentration of this guy. Okay, right, and by the way, they told us that it is titrated, so we are able to obtain that a little bit later on. Right, so they say to us a balanced equation for the reaction is given. Okay, the results of the titration, right, are given below. Now, in run 1, we are given the volume of hydrochloric acid. So, because potassium, potassium carbonate is a titrant in this case, we are going to put it in that burette of ours and allow it to drip. And so we started with 6.5, right, cubic centimeters, right? And in this case, we want a final value, okay? So we started with 6.5. Now they said to us the volume of potassium carbonate that has been used was 20.05 cubic centimeters. Okay, so we know how much of it we actually used, right? So in this case, we started with a certain amount. Now, the problem sometimes, guys, is with the type of burette that you would have used. Some of the burettes start with 0, right? And in this case, end with, they go higher as you go down. Some starts with a higher amount and go down and go lower as you go down. But it seems in this case, when I look at this burette, right, you start with a lower mark. Let me just show you what that looks like. So if this is your burette, you started at a mark of 6.5 and you use up potassium sulfate. So this is initial, okay, and you use up potassium carbonate, but at the end, you've got a certain amount. Now we need to find out what that amount is. But we realize that the volume that we've used, so we need to find out what the final amount is. But we realize that the amount that we've used was 20 cubic centimeters, 20.05, okay? Now, so you can say volume final minus volume initial will equal to the volume that you used, okay? Now, in this case, I want you guys to please note, because my final amount, these values are actually increasing as we go down. So the amount at the bottom is, in fact, they are decreasing rather yes, they are increasing as we go down. So the amount final, okay, which is what I want, minus the amount initial, which is 6.5, will give me the amount that I've used, which is 20.05. So that tells me what that amount should actually be, okay? So that tells me that the final amount must have been 26.65. I hope that makes sense, guys, right? So that's 26.65. So they said determine the value of P. That's 26.65. Okay. And then what about Q? We are going to do exactly the same thing. Sorry, that is cubic centimeters, right? We're going to do the same thing. In this case, we're saying the final minus the initial will give us the amount that we've used. Okay? Final amount we do not have. Initial amount, or rather actually the other way around. The final amount we have, which was 48.3. The initial amount we didn't have, which was Q, will give us the amount that we used. Okay? So to get the amount that rather we started with, we'll say 48.3 minus 20.145 rather. 48.3 rather, minus 20.15. That will give me my Q value. And so my Q value is 28. Okay, 28.15. That's 28.15 cubic centimeters. I really hope that this makes sense, guys. So this, I think you just needed to use a little bit of logic, but also the assumption is that you've done a titration reaction before and you would be able to get those values. Right, now they say to us methyl orange is used as an indicator, right? Explain why methyl orange is the most suitable indicator for this reaction by referring to the pH of at the equivalent point. Now, I want you guys to please note, potassium carbonate is a weak base. We are reacting it with a strong acid, right? So a strong acid plus a weak base will give us an acidic salt, right? So in this case, our pH should actually be less than 7, okay? So methyl orange has a pH range, right, that is less than 7, and so that is why it is a suitable indicator in that regard. Okay, I really hope that it makes sense. Okay, right. So let's go on to the next one. So they say to us, calculate. Okay, let's remove all of this. Now they say to us, calculate the concentration of potassium carbonate solution, right? So how can I get that concentration? Well, I want you to think about it. I know the volume of the acid, okay? Did they say for which reaction? Well, it wouldn't matter. Let's take for run 1, right? I know the volume of the acid, and I know the volume of the potassium carbonate, right? So I'm going to use my CaVa over CbVb formula, and that will be Na over Nb. Now, guys, I want you to note the concentration of our acid was given to us as 0.1, right? Now, very important, concentration of the acid 0.1, the volume of the acid, sorry, I'm just going to try and make some space here. So CaVa over CbVb is equal to Na over Nb. Right, so that's 0.1 multiplied by the volume of our acid. They told us we use 25 cubic centimeters. Now, I'm not going to convert it, provided that both the acid and the base are both in cubic centimeters, right? And this would be divided by the concentration of the base, but that's what we're looking for. The volume of the base that we used for experiment 1 or run 1 was 20.05. That's in cubic centimeters, so that's why I said I will not change that. So that's 20.05. Okay, now very important. Okay, that's going to be Na. Now, where do we get these values from? So this I get from the reaction. My Na value, that's the number of moles of the acid, right, in that ratio. The number of moles is 2. Okay, all right. Thank you to my technical team for the day. Right, so 2 moles in this case, and the number of moles for potassium carbonate would be 1. So in this case, I know that I've got number of moles, which is, for acid is 2, and for the base, this is 1. And guys, we are just going to do our mathematical gymnastics, right? So that's 2 times 20.05, we cross multiply, times Cb. Okay, so I'm going to say firstly, 20 times 2 times, that's 2 times 20.05. Okay, that's 40.1 Cb is equal to 0.1 times 25, that would be 2.5. Okay, times 1. And of course, you'll divide both sides by 40.1, 40.1, and the concentration of your base. Okay, 2.5 divided by 20.1, and I get a value of 0.12. Okay, right, that's moles per cubic decimeters. Right, I hope that you guys can see this. All right, so that's 0.12 moles per cubic decimeters. Right, and remember, we only use this formula, guys, when they have told us that we are either titrating or when they tell us that the reaction reaches the end point. It means exactly the same thing. Right, so we get a concentration of 0.12. Now, let's go to the next question, a very interesting one. Now, we've gotten the fact that this guy has a concentration of 0.12 moles per cubic decimeters. So they say to us, the above reaction, I'm just going to remove it now. Okay, let me see if... Kwena says, saying ready. All right, I'm glad to hear that. So can you please explain 7.3.2? Okay, I'll go back to it. immediately when I'm done with the next one that I'm going to do. Nah? Okay, right. So now they say to us, calculate the value of X in the formula potassium carbonate, okay, with a hydrate. Oh, sorry, I didn't read the question. They said the above solution used in the titration was prepared by completely dissolving 6.525 of the hydrated potassium carbonate, okay, in 600 cubic centimeters of water. Right, very important, guys. So we know concentration is mass divided by molar mass multiplied by the volume, right? Now this is very important. In this case, we already know the concentration. That's 0.12, right? The mass was given to us, 6.525. Okay, right. I'm going to leave the molar mass for now, okay, so that it doesn't become too confusing. Let's actually get to find out what the molar mass is, right? Multiplied by the volume. Now, volume was given to us as 600. Remember, now you have to convert it to cubic decimeters, so that you divide by 1,000, so that would be 0.6. Okay, right. So that tells me, if I cross multiply there, so I will have, let's see. Okay, you can do that in your own way mathematically. I'm going to say 6.525 divided by 0.12 times 0.6. Okay, right. So I'm going to round this off. So that's 90.63 or 625 grams per mole, right? So our molar mass, please verify this for me, right? After you've cross-multiplied, I get 90.63 or 625 grams per mole. That's the molar mass, right? Now, I'm going to go there and say, well, how do we calculate the molar mass of this guy? So molar mass, we've got two potassiums, right? So we go to a periodic table. I forgot what potassium is. There, 39. Okay? So I'm going to go to my potassium there. So that's 39. So I've got two potassiums, that's 2 times 39, right? Plus carbon, that's 12, plus 16 multiplied by 3, okay? Plus, I want you to note, we've got X amount of H2O. H2O is 2 plus 16. So I'm going to say X times 18, right? 2 plus 16 for water. So plus X times 18. Why does it seem like that that amount is too small? 5 to 5. Yeah, I think I did everything correctly. Okay. 9.12. Okay. All right. So molar mass in this case. Now remember, this is all equal to 90.63. Okay. So let me see what we have on the other side. So we've got 2 multiplied by 39 plus the 12 plus the 16 times 3. Wait, I get a far bigger value. Because I've got 138 plus X times 18. Let me see, guys. I think I might have, I don't know if I, can you verify if I did that correctly in terms of my calculation on the other side. So concentration mass at 6.525 divided by, this was 0.12 times 0.6. Yeah, I still get the same amount, 90.625. Yeah, so this is how you would have actually had this question. So you're supposed to get a higher molar mass so that you can be able to determine in that case the concentration. Let me just see quickly if there wasn't any other information. All right. Okay. Yeah, we did find the concentration of this guy. Okay. All right, guys, I'm going to leave it like that. I'm not sure if perhaps there might have been a mistake that I might have made in the calculation of the 0.12. Good titration. Did I make a mistake on the titration? Was it supposed to be 0.06? All right. So I'm trying to check. So this was supposed to be 0.0. Oh, I see. I see. Okay. Guys, I'm not really sure if I understand, but I see some of you are showing me 0.001, and I'm not sure where that features in. Okay? But I suppose you get the gist of how to get to go about this question, right? I think for the sake of time, so that I'm able to accommodate something else. I hate it when that happens. I think the calculation that we did prior was correct, okay? But I think please just check for me and verify where I might have went wrong. Okay, I'm just trying to check as well from your comments. Okay. All right, but it's okay. So you get the gist of it. So what you would actually do, right, if you take this to the other side and you would divide by x, right, that should give you the value of x that you'd get for your waters of crystallization. That's what we call it. Nah? We call that waters of crystallization. And it should be a nice round value, okay? If you don't mind, maybe I can come back to it. I will go to 7.3.2, okay, that I was asked to actually do. Now remember, what I said is that you've got an initial value for the burette, you've got a final value for the burette. So this value here, the final value minus the initial, must give you the volume that you actually used. So what I said is that the 48.3, which is the final value that I read on the burette, minus the Q value, which is the initial value that I would have gotten from the burette, will give me 20.15. That's how you do a titration, right? And if I if I take Q to the other side, I'll have 48.3 minus 20.15. Okay, and I got that value to be 28.15. I hope that makes perfect sense. Okay, so this gives us a little bit enough time. What I'm going to do, instead of looking, I think you guys are more or less very good usually when it comes to question 8, which is electrochemistry. So what I'm going to do, I'm going to go to reactions in organic chemistry, which in my opinion is really, guys, you want to maximize on that organic chemistry. So please take a look at it and make sure that you do that very well. Okay, right, now let's go for question 4 because we've got time. All right, let's go for it. All right. All right, I'm still trying to see, maybe for those of you who'll do this much later, you'll let me know where I might have gone wrong in terms of the previous one, but at least you've got the idea of how to go about it, okay? Right, now let's go to the next one. They say reaction 1 is a cracking reaction, right? Forming two organic compounds, W and T, as the only products. Now, remember, whenever we are cracking, we are taking large organic molecules, large organic compounds. You are forming smaller, more usable compounds, right? You can either have catalytic cracking or you can have thermal cracking, right? Now, they said define the term cracking. I've just explained it. Now, in this case, it's breaking down large organic compounds to form smaller, more usable ones. And in this case, they said in 4.2, is the product in reaction 2 a primary, secondary, or tertiary haloalkane? Now, let's do this. So, we took whatever reactant was at what that is W, right? And what we now formed for reaction 2, we reacted it with something, and remember, for cracking, we'll always get alkanes and alkenes, right? Rather, let me say alkanes, alkenes, so we actually get hydrocarbons. So when we went through reaction 2, I realized now there's a bromo there, and it tells you, okay, I must have actually reacted this with bromine, okay? Now, if it was an alkene with a double bond, I would have been able to have two arms available and have both bromos being attached, but there's only one here. So this does tell you this must have been, so this guy must be an alkane. It underwent a substitution reaction, okay? So they wanted to find out, in this case, is the product in reaction 2 primary, secondary, or tertiary? So you've got that bromo at the end, okay? Right, so it is a primary haloalkane. And what is the reason for that? That the bromide ion is at the terminal carbon, or what you can say is that the carbon that has the functional group, which is the bromide in this case, is at the end. Okay, right, so this is the carbon at the end. All right, now let's go to the next one. They say write down the structural formula of compound W. Now I've just said it to you right now. We realized we had bromide over there, right? So if I take it back, it must have been an alkane. And what alkane was it? Exactly what we have. So CH3, CH2, CH2, and at the end, CH3. So this must have been, in this case, butane, right? So they said write down the structural formula. So the structural formula for butane Okay, there we have it. We've got all our hydrogens over there. And please forgive me, ladies and gents, I don't have enough space, so some of my writing will spill over into the other parts. Right, now they say to us, the molecular formula of compound U, right? So what did we do for compound U? You can see we had C4H8 that was formed, but we also had C4H10. Okay? So, what was compound U? If you take those together, 4 carbons, that will give me 8 carbons. Hydrogens, you've got 8 and you've got 10 here. If you add them together, they'll give you 18. So, actually compound U is petrol, octane gas, right? Octane, which is petrol, right? The one that we use to fuel our cars. So that's actually octane. All right, so let's go to the next one. They say for reaction 2, write down the name of the formula of the inorganic reactant. Okay, so the name of the formula of the inorganic reactant for reaction 2, we noted there, we reacted it with bromine. So you can either write the Br2 or you can write bromine. Please note when they say name of formula, right, or when they say molecular formula or the structural formula in that case. Right, now they said to us the type of reaction, okay? Right, that is in reaction 2. So we noted in this case that we only added 1 bromine, so it must have been a substitution reaction. We took a saturated hydrocarbon, right? So substitution. So remember, if it was an alkene, we would have added both of the bromines, right? Okay. Right, so they said, so we know it was substitution. Right. And they said to us 1 reaction condition. Okay. So remember, whenever we are adding, right, bromine, in this case, it has to happen in the presence of UV light. Okay, so we usually use UV light because remember, that is a non-spontaneous reaction, right? And as a result, you need to kind of stimulate it, so we use UV light over there. Right, and let's go to the very next section. Now they say to us the diagram, the flow diagram on page 9 is redrawn below for easy reference, right? Organic compound U. Okay, it's actually exactly what we had there. Right, now they say to us, write down the type of elimination reaction. Write down the type of elimination in reaction 3. So let's look at reaction 3. So how do we know what reaction 3 is? Right, so we're going to have an elimination reaction. Okay, so we're probably going to remove bromo, but remember, if it's an elimination reaction, we're going to remove the bromide ion together with one of the hydrogens, okay, so that we end up with an alkene. So in this case, it's going to be dihydro. Okay, my pen is doing some funny stuff now. So this is dihydrohalogenation. Okay, we remove the halogen, we also remove a hydrogen. Right, now they say to us compounds R and T are positional isomers. Okay, R and T, where is that? Okay, all right, so they said they are positional isomers, right? So which means this guy is also C4H8. The only difference is that we know we are going to have here, so if we were to draw it in structural form, that double bond is going to be at the first carbon, right? Yeah, it's going to be at the first carbon, and in this case we end up with a structure that looks like that. Now for this to be a positional isomer, it can only mean that it's actually at the second carbon. I hope that makes sense, right? The double bond is between carbon number 2 and carbon number 3. Now they say to us, the inorganic reagents shown below are available for reaction 4 to 5. Shoo. Right. So we are taking this guy, which was a primary which was an alkene, and what do we need to do now? So what we can do, and I want you guys to please just note this. I'm only going to try to explain this to you. So it was a primary, or rather it was a haloalkane, rather not a haloalkane, an alkene, which was at carbon number 1, right? So we need to now react it with something that's going to break that double bond, right? But once it breaks that double bond, we are now going to form another compound, right? So what I'm going to do is let me react it with sodium, let's see. No, that's going to be elimination, concentrated sodium hydroxide. Okay, so you know what I'm going to do? I am going to react it with hydrogen bromide, okay? Right, so plus HBr. Now stay with me, guys. So this will form, I want you to note, the bromide, so we are going to apply here Markovnikov's rule, right? And Markovnikov's rule simply says the hydrogen, right, in an addition reaction, the hydrogen will go to the carbon that has the highest number of hydrogens. So the bromide will go here, right, in reaction number, in carbon number 2, when we break the double bond. We've got hydrogen, hydrogen, hydrogen there. Okay, and the bromide will stay in carbon number 2, right? And now what we are going to do is we are going to react this with concentrated sodium hydroxide, which is now going to eliminate that hydrogen bromide and react or result in that compound that we have, which is T. Okay, so they said to us, write down a balanced equation for the reaction in 4 using structural formulae, right? So what did I do? I said to you, we're going to have this kind of a reaction. We knew that we had an alkene, right? I want us to move towards finishing. We had an alkene. And now, what did we do? We broke the double bond by reacting it with hydrogen bromide. And so, what did we do here? Right? So, we ended up with applying Markovnikov's rule. We had hydrogen, hydrogen over there. And we said the bromide is going to be at carbon number 2, right? Because hydrogen has to go to carbon number 1 according to Markovnikov's rule, right? So that's the reaction that took place in reaction number 5. Okay, right. Now they say to us the balanced equation, in number 4 rather, the balanced equation for the reaction 5 using structural formulae and correct reagents shown above. So for reaction number 5, what we said, we are taking that guy, the one that we got from reaction number 4, and we are now reacting it. Please, I want you to note, we are now reacting it. Right. We are now reacting it with concentrated sodium hydroxide. Okay? So they did say this is concentrated sodium hydroxide. What we are going to get, ladies and gents, on the other side, this forms an elimination reaction, right? So the hydrogen, now we are going to apply Zaitsev's rule here, okay? Now maybe let me do this. So Zaitsev's rule says the hydrogen, we are now going to take the hydrogen from the carbon, with the least amount of hydrogens, right? So we have hydrogen, and we'll have a double bond over there. Okay, right, so this is what we are going to form, but please, I want you to note, we've got byproducts, which is going to be the reaction between hydrogen bromide and sodium hydroxide, and that will mean that we are going to form sodium bromide plus H2O. Right, sorry that I don't have enough space in which to cover this. And they say the IUPAC name of compound T, okay, compound T, the IUPAC name is going to be but2-ene. All right, I hope that has been helpful. Right, ladies and gents, I would have loved to cover the rest of the other sections. I think that for the purpose for why we met today, right, we were able to cover, as much and wide. Yeah, I think the last two sections, you guys, electrochemistry really is one of those sections where you can actually get some good marks. Please look at the method that I have used. I'm going to close our session a little bit earlier in this case. Please just note, guys, that we do have a course on NBTs for those of you that are already writing NBTs. Our course is only 350, and if you use the code, I forgot the code, I think it's Malume11, right? You can even get yourself a discount in that case, and it makes it that much more affordable. You know, guys, that NBTs are really expensive, but I do also encourage you to join in as a member, because we are going to have live lessons, right, between Mondays and Wednesdays. That will be exclusively for our members. For those of you that really do want assistance in maths and science, we've got the academic bus that is also there. And I really want to thank you guys. And please, in future, you can even bless us. We do need all the funding that we can get. Okay, so if you really want to contribute to this channel, right, you can do so through what do they call them? Super chats and super stickers, right? You can contribute to that, but you can also just find out more ways in which you can contribute. And finally, I just want to say, in June, we will have our camp that will be running from the center, but we also have that same camp. It's workshops, actually, that we are doing for maths and science. For those of you that are in Matric, you're welcome to join those. For more information, you can just get in touch with us. It's info@mlungisinkosi.co.za. All right, that workshop, it's only 350 per workshop, and that's a whole day event, guys. That will take you, we'll be doing paper 1 on day 1 on maths, and we'll do paper 2 on maths the whole day, and we'll do paper 1 on physical science on on Wednesday, and paper 2 on physical science on day 3. So guys, it's really been a pleasure. Thank you so much. If you want to know also, we've got classes. We had our Saturday sessions right here running at the center, but we do also all our sessions are also online, so you are more than welcome. It doesn't matter where you are, you still will be able to get through to us. Right, so if you need any assistance, guys, we are more than willing to do that for you. From me for now, it's really been a pleasure. Thank you so much for lending us an ear, and I wish you all of God's best as you are going to be writing on Monday, for those of you that are writing. And for those of you that will be writing your June exams that are in Matric, please, I wish you all of God's best. We will have more of these live sessions, right, in the future, and we are hoping for more partnerships to help us run these live sessions. Otherwise, from me for now, I'll see you guys again next time. Sharp.